For this problem, we got a little bit of foreshadowing of what's to come. We're going to be looking at lots of tables of data in this unit and doing a lot of work with that. So we've got this point here that most experienced runners get a point where they can comfortably jog long distances at a consistent pace. I think experienced runners would also object to the word jog. They run at a consistent pace. So this pace is another way to say rate of change. Because speed is a special type of rate of change. It's a distance compared to time. So one particular runner runs one lap around a 400-meter track in 2 minutes. Okay, so there's the top value and the bottom value. And we're going to assume that this runner can maintain that pace forever. So for every 2 minutes, the runner runs 400 meters. So we're going to complete the table to fill out this pattern. So if we've gone 4 minutes, that's another 400 meters, so we would be at 800 meters. And I believe he just wants us to keep this distance the same every 2 minutes. So 4, 6, 8, 10, 12, and then we're just adding 400 each time. Doesn't that sound interesting? It seems like when we have constant addition, there's a linear relationship between these data values. Now we have to be careful because we have a change in the x values, a change in these values. Oops, I'm getting ahead of myself. That is not steps of one, not units of one. So we'll talk about how to handle that in the next unit. So notice that this rate of change is constant. So when the change is constant, the quantity illustrates what type of growth. Oops, we already said that. That's linear growth. So we're going to write this as a fraction, and we want meters in the numerator. That's most often how we think about it, although I think some runners like to think about minutes per mile or as a pace. So one of the things that can be tricky about this is the abbreviations you use for the units. Our textbook, and it's very common throughout the scientific and mathematical world, to use an M for meters and an MIN for minutes. Easy to confuse, right? Okay, so this is the rate. If we want a unit rate, that means we're asking for meters per 1 minute. So we're going to divide the top and bottom by 2. That's not too difficult for me to do at this point. I feel good about that. So they're really traveling at a rate of 200 meters per 1 minute. So let's convert that to per second, meters per second. Now, we live in America, and so Americans would probably prefer to see that in miles per second or feet per second, since that's how all of our signage and most of us are programmed to think from elementary and high school. But we'll leave it at this. So we're starting with this rate. Notice what's different about this dimensional analysis from the previous work we did in chapter 1 is that our starting value has units on its denominator, where before it was just convert 200 meters into miles. And there was just 200, and then we did conversion factors along the way. So for this one, we're taking these 2-unit things, and we're wanting to end up at the very end is meters divided by seconds. So all we have to do is consider how many seconds are in a minute. That conversion factor is, well, the equivalency statement is this: 1 minute equals 60 seconds. And since we want seconds in the denominator, I'm going to put the 60 seconds here, and I'm going to put the 1 minute on the top. That way these cancel, and we're left with exactly what we want. Now, I'm not so great at 200 divided by 60. Maybe I should be. But listen, there's no shame in using technology. So we get 3.33333, right? So, well, let's write it exactly. 3.3 repeating. That's the exact value, and that is minutes per 1 second. Unfortunately, doing calculations, we need all those 333s going on forever and ever and ever. So this is just notational. That I don't know if you remember this from an earlier studies of math. That line over the 3 says repeat that forever. Okay, so what distance would the runner cover in 40 minutes? All right, well, let's work with our 200 meters per 1 minute. The reason I'm choosing that unit rate instead of the seconds one is because we're given time in minutes. So I'm going to multiply by this 40 minutes, and its denominator is 1, so that 40 is in the numerator. And these just cancel, and we've got the number of meters they travel. So 4 times 2 is 8, and then there's 3 zeros, so 8,000 meters. Well, what distance would they cover in 40 seconds? Okay, so this one, it's going to be better to use the 3.3 repeating minutes. Who said minutes? Meters per 1 second. And we'll do the same thing we did here. We're going to multiply by those 40 seconds. And seconds cancel, and we're just left with the number of meters traveled. Now I'm going to use my calculator and check out what I'm going to do. I'm going to keep the fraction that I used to get the 3.3 repeating, and I'm going to multiply that times 40. And that gives us exactly the value we want, 133.3 repeating meters. Again, I haven't rounded this number yet. By the way, I've written it because of that decimal. When you work in ALEKS, I think sometimes they give you the option to put that in there, and other times they're going to say round to a particular value. So pay close attention to what ALEKS is requesting the answer to be written as. All right, so what would this runner's total time be for a 10K race? Ooh, okay, so 10K means that's slang for 10-kilometer race. So what we're going to do is take this distance and we're going to divide it by the rate that this person is running. And that will get us our time. Now, we can do some analysis of those fractions of why that works, or we can think about distance equals rate times time as that distance formula, and that if we solve that for time, that's equal to distance divided by the rate. So what I think I'll do is I'll just write this as multiplication of this 200 meters over 1 minute. I'm just flipping that fraction, which is what happens when you divide by a fraction. You flip and multiply by the reciprocal. Now the problem is we can't cancel out the kilometers and meters, so we need to note that 1 kilometer is 1,000 meters. So I'll just tack that conversion factor on at the end. I want to get rid of these meters in the denominator, and I want to get rid of those kilometers in the numerator. So there it is. Now it might have made more sense to start by converting this thing at the beginning, so moving this first and then multiplying by that rate. But you know, in multiplication, it doesn't matter the order you multiply things. The result is unchanged. Okay, so here's our value. Check out this mental math. I can cancel 2 of these zeros with 2 of those zeros. And 10 divided by 2 is 5. And so we're left with just a bunch of 1s in the denominator, and they're all unitless. And in the numerator, we're left with 5 times 1 times 10, and the only units that are left are minutes. So it's going to take this person 50 minutes to run a 10K marathon. That's not a marathon, a 10K race. A marathon is like 22.4 miles, which is whatever kilometers. All right, let's do one last problem. And that is, what's up with the Earth? Okay, so the Earth moves at about 98,000 feet per second as it revolves around the sun. So here's that rate. How fast is that in miles per hour? So note that we're converting 2 things in this unit rate. We're converting the time into hours, and we're converting the feet into miles. So let's do the miles into feet, or the feet into miles, excuse me. So 1 mile. Now notice my abbreviation for mile is MI. My abbreviation for minute is MIN. And my abbreviation for meter is M. It's really easy to get confused. Okay, so pay close attention to that as you're working with these. And if it's helpful, don't be lazy like me. Write out the whole number. Write out the whole word, MILES. Okay, so 1 mile is 5,280 feet. Notice what's going to happen here is the feet cancels, and we're going to be left with miles per second. So let's now multiply by how many seconds are in an hour. Well, maybe it would be easier to use two conversion factors. I know that there are 60 seconds in 1 minute. And then I also know that there are 60 minutes in 1 hour. Now let's confirm that I've actually set this up correctly. So these seconds here are going to cancel with the seconds over here. These minutes are going to cancel with these, and we're left with miles per hour. All right. All we have to do is multiply everything out in the top and everything out in the bottom. I don't see a whole lot of awesome canceling that I can do like I did in this other problem. I mean, I could get rid of one of these zeros, but it's not super helpful. I'm just going to type this whole thing out. So 98,000 times 60 times 60. And then, ooh, look at that. I hit division, but I didn't put in parentheses, and it's going to divide just the 60 by this value. That would give me the wrong answer. So I've got to do the parentheses, then divide, and Desmos makes that nice fraction. And we're dividing by 5,280. And there's our result. We're hurtling through space all around this value. Well, I don't need to. We're hurtling through space at a rate of 66,818.18 repeating miles per hour. Seems kind of fast. If we were to stop abruptly, all life would cease to exist if our planet stopped its movement.